In general, if you have variables that are not lower bounded, you should put a minus infinity here. If you want to refer to the probability of not exceedance, I mean, you have to refer to minus infinity. And then if you compute the integral between, let's say, minus infinity of whatever and an upper value of the density, you obtain the cumulative probability, which is indicated here as a capital F. And here it is written that the capital F is given by the probability of a generic value of x be lower than. So it's expressed as a probability of not exceedance. And just be careful, if you want to compute the probability of not exceedance, I say again, the integral must be computed between the lower value and the generic x. In this case, the lower value is 0 because I assume that we are dealing with river flows. In the general case, the lower value will be minus infinity. This is what I need. And in order to give you a first reply, the literature gives to me some solutions for F. Some solutions which are called probability distribution functions. So basically, they are called probability distribution function, PDF, for the density, and they are called cumulative distribution functions for the integral. So again, the literature gives to me some functions that I can use. But you understand that these functions, if they are general, if they are given by the literature, it means that they can be applied to different processes, different rivers, for instance. And therefore it means that these functions should have some parameters in order to give some flexibility. Like rainfall runoff models have parameters to be calibrated in order to be applicable to different catchments, even the probability distribution functions have parameters that must be calibrated to be applicable to different catchments. And you see the analogy, the probability distribution function which takes the place of the rainfall runoff model that I considered before. And the rainfall runoff model that I considered before was a one-to-one relationship between input and output. In this case, I have a probability distribution function which gives to me the probability of the output. So it's not much different. Still, I have the problem to solve of the memory of the process, which is not solved yet. But if we could consider a river flow, a river whose flows are independent, meaning that if I go today, the observation that I see today is completely disjoint by the observation that I can see tomorrow and the observation that I could see yesterday. If I had a river flow, again, a river who is completely independent, then the probability distribution function would completely substitute the rainfall runoff model. It would be nothing else than a rainfall runoff model formulated in a different way. We have the problem that, you know, the probability distribution function, because it just looks at the frequency of occurrence of numbers, doesn't keep memory into account. So let me give you an example, because this is, and then I stop. This is what we will discuss tomorrow. Because we can understand that the probability distribution function is an analogous of the rainfall runoff model, but the probability distribution function, as I said, it's just estimated by looking at the frequency of occurrence of data. So let me make you an example now. Let's suppose that I have a hydrograph. Q depending on T. And let's suppose that it's in a yearly hydrograph, yearly and daily, meaning that, sorry, it's a daily hydrograph which has a length of 1 year. So, if you look at it, you see something like that for in our climate. So you have like in May, you have a peak, and then you have a drought in summer, and then in October you have another peak. Fine. Now let's suppose that I take these numbers, the same numbers, Q, T, and let's suppose that I shuffle them. Shuffle means that I'm mixing. Like you get some cards and you shuffle the cards before playing. Then, if you take this number and you shuffle them, you obtain a completely different hydrograph, and which would look like something like this. And in shuffling, you destroy the memory, of course, because now each observation is completely independent by the past and the future. You destroy the memory. But if you compute the probability distribution of these two series, they are the same. Because, you know, of course, if you look how frequency of occurrence is defined, you just count how many numbers fall in each river flow range, and you compute the probability distribution. So basically, if you shuffle, you don't change the probability distribution, but you completely destroy the memory and you obtain a different process, which means that the probability distribution alone is not enough to describe this process. You need the probability distribution because it describes how much likely is an event, but you need some more in order to take into account that here there is a memory. And this is the problem that we have to solve before saying that we found a substitute of the rainfall runoff model. The probability distribution alone is not a substitute. Tomorrow I will again teach and I will continue, and basically I think by tomorrow we get close to the end of this. So if you're really bored, please be patient, and you won't be bored for a long time anymore. And bring also your PC, because I think the best way to learn how probability works is to take some numbers and make some experiments. So we want to develop an exercise, but I will show you some computation over the screen. If you don't have the PC, you can just follow me, but it's better if you take your PC so you can yourself make the same experiments. And again, it's not an exercise, it's just an interaction that we have from the PC to play with the data. And if you have any questions on this, I am aware, fully aware, that this is a lecture that is not easy to follow. So just let's discuss now or tomorrow, maybe better tomorrow, because you get some time to think to it. And then, okay.